I don't know. Okay. Now you've got this concept that you've got this star. Surrounding the star is, you can imagine, a sphere, right? And all of that power, all of this power, is spread out now over the sphere. And the sphere, of course, has an area of 4 pi, and well, the distance we are from it, right? Okay, so we are some distance d from this thing, right? And so the apparent brightness, which is a lowercase b, is just the luminosity, right? So it's this guy divided by that area 4 pi d squared, like this, right? So the L, it should say L is spread out over a sphere. I think I'm finding a lot of mistakes today. I should write these down. I won't remember too, yeah?
I've already said this, but I probably did listen. Are these in the data packet?
These are, yeah. These are. I'll show you the ones that aren't. Okay.
You never know.
And then on the note guide, it's meters Kelvin. Right? There we go. All right. So here's a little picture that shows you this, right? This is the inverse square relationship. Here is this point that's emanating light, right? If we're 1 unit away, then this thing is spread out over 1 square unit. If we're 2 units away, it's doubled the length of both sides of this. So it's now 4 times as much area. And then if it's 3 times as far away, it's tripled the length of this, because it's just a simple thing, right? But since it's area, it's length times length, so it's squared, right? And they love this. IB loves this. They love this relationship and this relationship. So if you do paper 3, and after today, you can start working on paper 3. There's lots of questions in paper 3 if you're working along on last year's test. You can do that section, right? And as you do those tests, if you can't get it, just cheat. Just look at the answer and go, oh, look at enough of the answer. Go, oh, okay, and then just work it out yourself. Yeah, well, you can this time, right? We're just trying to, by the 27th of this month, you want to be through those tests, right? Put this in your notes. Our sun puts out about 3.87 times 10 to the 26 watts of power. We're about 1.50 times 10 to the 11th meters from it. What is the apparent brightness? So this is the watts per square meter, right, of the sun at the Earth's distance, right? So this isn't too hard, right? B is just L divided by 4 pi E squared, right? So that's going to be to 3.87 times 10 to the 26th watt light bulb. And then we are that far from it, right? It is 3.87. $1368.73, blah, 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 right? And this is watts per square meter. So literally, this is where physics leaves off, right? If physicists would leave it this way, this is watts and square meters. We're going to get into like magnitudes, which are arbitrary scales that astronomers have used, okay? But this is it, right? Is that we end up with watts per square meter. These are good straight up physics units. This is how much power you could get. If you put a solar panel above the Earth's atmosphere, right, because below the atmosphere it's somewhat less, you could, if it was 100% efficient, that's how much power you could generate with a square meter, right? They're not 100%, they're like 20, 30%. Yeah. Yeah. If you could concentrate, but that'd be incredibly concentrated, right? It'd be very collimated or something like that, right? Okay. Now, the interesting thing here is if we could look across, and this is where we're headed, okay, for the rest of today, okay, is that if we could look across and look at a star, say in another galaxy like Andromeda or something like that, and we could tell somehow by looking at that star what B is, yeah? Or I'm sorry, what L is. Right? If we could look at the star and go, oh, that star, that kind of star is a 5.8 times 10 to the 30th watt star. Right? If we could tell that, we can measure this. This is something we can measure with incredible precision here on Earth. We got these little brightness measure things. I don't know, right? Okay, so we can measure this. If we know this, what can we figure out? The distance we are from the star, right? So if I give you guys all light bulbs of the same brightness and you stand different distances out in the parking lot, all I have to do is just take a little photometer and just point it at you, and by measuring your brightness I can tell how far you are away. This is a very, very important thing. Almost all measurements of astronomical distance have to do with this, beyond parallax, right? And then how you figure that out, you know, like, okay, parallax and then brightness, right? We'll spend a whole day on that. All right, hey, let's try this. This is a key concept. A photometer, by the way, is what those, you know, when photographers walk up and you're sitting there like this and they got the lights shining on you and then they take this little thing and they just point it at you. Okay? That's a photometer. They've got a little brightness meter and it's saying how bright your face is, right? And this is very, very important. Like when they do film and stuff like that, they actually do lighting sessions. And they've got people that look kind of like the actors with the same sort of skin, right? And they have them stand in for these lighting sessions where they figure out how to light every scene so it looks nice. Yeah? Well, otherwise, I mean, that's why Hollywood videos look so good. That's right. Because somebody's spent, you know, I mean, I don't know what it is, what the ratio is, but lighting doubles. That's right. Have you guys seen Love Actually? Yeah, and then what units? That's right. Have you guys seen the movie Love Actually? There you go. Don't tell your parents I recommended it. Notting Hill. Yeah, I'm not recommending it on YouTube. Okay. Notting Hill. Have you guys seen Notting Hill? 3 weddings and a funeral. Was it 4 weddings? I don't know. 3 weddings? These are all beautiful movies. I can't tell you. This is probably my favorite one. It's just vignettes about love. Different kinds of love. Yeah, that's right. You guys haven't seen it, really?
Never even heard of it.
What? Yeah, it's just an odd. You've seen it? Yeah, the reason I'm bringing this up is that one of the love scenes are there's a couple that start out they meet each other. That's right, because they get a job as lighting doubles for a porn film.
Nice.
I was confused. Why were they talking to it the entire time? Because I was like, what kind of video would it be?
They're the doubles, so it's a lighting session.
Oh, I see.
They're not filming. The guy's just sitting there measuring the lighting because, yeah, didn't know. They're not the actual stars. They're just the stand-ins. Yeah, meters. Don't get all your points. There you go. Is anybody still working on this one? Are we good? 1.3 times 10 to the 17. You got that? You're the man. All right. Now we're done with physics. Now we're going to get to apparent magnitude. Okay? Now we're going to get to apparent magnitude. And this is an astronomy thing. Why astronomers use this scale, I don't really know. Okay? But apparent magnitude is this thing where if you look out at your eyes have this crazy ability to see a huge range of brightness and just put it all in scale. And so